Yes, I think now it is recording. So what I was discussing, there are two things. So one is the design dimension. Okay. Then there is the product dimension. So what happens that whenever we design any product, so we in terms of, I'm talking here mostly from the mechanical aspect perspective. So we take care that whatever stresses will be generated in any product. So the dimension of the product or the material which is there in the product, it should be sufficient to bear those stresses. So let me come to this topic from a very basic understanding that what are stresses. So stresses are nothing but these are the internal response of a material to an externally applied load. So whenever a material or a product is loaded externally, so stresses are induced in that material which are in a response to the external load. So talking it in a very simple way, so whatever stresses are generated in the elastic limit, these are taken care by this very famous relation. You might have also read it earlier in high school. It's known as the Hooke's law. Means stress which is induced in the material, it is directly proportional to the externally applied strain within the elastic limit. Now, for any material or any product, the stresses which are induced, so to counter these stresses, the product is made up of certain material. We have seen an overview of this different type of materials in the IC 141 course. We have discussed different type of materials, for example, metals, ceramics, then polymers, then composites. So what happens, I may design a certain product. For example, I'm looking to design a shaft. So we have just seen the shaft couplings. So I'm just looking at that. I have designed a shaft. So shaft, say I have designed shaft of 25 millimeters. Diameter of the shaft is 25 millimeters, which will be carrying, say, a certain amount of torque. Say it is carrying 100 Newton meter of torque. So this is what my dimension says. So this is from the design aspect. I wanted to transmit a torque of 100 Newton meter, and I'm not going into how this 25 comes, but yes, you will learn about this in future courses in the mechanical engineering. But what you need to understand is, for this 100 Newton meter of torque, I want to use a shaft of 25 millimeters. Now, to produce a shaft of 25 millimeters, what I am going to do is I will take a round bar. Okay. What I am going to do is going to take a round bar and I will do the cylindrical turning on that using a lathe. So I will take a bar and I will turn it by doing the turning operation on a lathe machine. So you have also read about the machining process. Machining process is basically a process to remove excess material from any given workpiece. In generally a lathe machine, it comes in the category of conventional machining process where there is a physical contact between the tool and the workpiece. Now, what is going to happen? This bar may, for example, I take this bar which is stock of say 30 millimeter diameter. So diameter is represented by this phi also in many drawings. So phi is basically the bar diameter is after turning. The initial diameter was 30, so after turning from the lathe machine, I obtain the diameter of 25 millimeters. So this is an ideal scenario. It's a very, very ideal scenario. But that will never be the practical scenario. In practical scenario, what is going to happen? I may target 25 uh, millimeters as the dimension, but I am never going to achieve it. So I may achieve, I may achieve 24.995, or I may achieve 25.010. Okay. but it is very, very hard to get every time 25.00000 and so on. Say for engineering perspective, we can consider up to four or three. Generally, what is considered is three places after the decimal. So it is already in millimeters. So we are looking at the microns from here, or the micrometers. So this was, what was this? This was the product. Sorry, this was the design dimension. So this was the design dimension. But what I'm obtaining, sometimes I'm obtaining 24.44995, sometimes I'm obtaining 25.01. So this become the product dimension. Now what is the catch here? The catch here is that we are deviating from the design dimension. So now this deviation from the design dimension, that is deviation from this 25.00000 millimeters, and this is the deviation here, 0.01 or minus say 0.005. So this deviation, it can be tolerated to a certain extent, beyond which it cannot be tolerated. So what is going to happen beyond a certain extent? We will say that the product is undersized, the shaft is undersized, or it is oversized to be put in practical use. So production drawings, they deal with these aspects, how to represent these aspects for the shop floor person or the person who is manufacturing. They should know that if they are making a shaft, from the drawing they should know what is the deviation or acceptable deviation in the dimension which is possible. So I hope some understanding is there. Now you have some understanding that how production drawings are different. What earlier we were doing, what you were doing is you were just making the dimensions, or you are just making the dimensions, say for a bolt or a shaft. So I'm giving you to draw a shaft, you will draw the shaft, okay, and you will tell that the diameter is say 25 millimeters. But in production drawing, okay, so you will not say 25 millimeters, but you will say 25 plus minus 0.002 millimeters. So this plus minus 0.002, how this is decided, from where it comes, what are the different reasons, and so on. Like, this is basically what is to be covered in this production drawing. And then we have to see that what are different aspects or different terminology related to this. So the least count of the measuring instruments, as I am showing here in this photograph. So I am showing you a digital. So you have a digital vernier calipers, okay, and I'm showing you here a ball bearing. So what is this? This is a ball bearing. This is nothing very specific. Just I'm trying to tell you is the least count of this digital vernier is 0.00 or 2 places after the decimal. But is the requirement really up to 2 places of decimal, or it is up to 3 places of decimal? So that aspect will come from the accuracy of the machine manufacturing process. So closer are the dimensions, or tighter are this the deviation. So this deviation, whatever this deviation is there, suppose I'm mentioning as mentioned here. So I am mentioning 25 plus minus 0.002 millimeters. So what is this? This is the acceptable deviation. So acceptable deviation will be, it is also known as the tolerance. Means we will accept the product to be fit for use if it is 0.002 millimeters short, or 0.002 millimeters it is oversized or undersized than 25. So this becomes the tolerance. So the tolerance is basically the tolerance from the or acceptable deviation from the basic size. So Here 25, it is denoted by another term which is also known as the basic size. So what this acceptable deviation is from where? So deviation has to have some reference. So that reference is from the basic size. So this acceptable deviation from the basic size is known as the tolerance. And you can understand if this tolerance zone, shorter is the tolerance zone or smaller is the tolerance zone, more precise will be your manufacturing process. So another, again, we are coming to two more important terms which many of you have some clarity or many may not have clarity, that is accuracy and precision. Another two terms which are coming into picture, it is accuracy and precision. So accuracy means you are always producing the exact same size, mean always equal to the basic size. So here we are everything referring with respect to the our terminology of machine drawing. So equal to the basic size. So if you are able to produce the diameter of the shaft equal to the basic size, your process is very accurate. But what is precise? Precise is repeating the same size. So which may be accurate or may not be accurate. Means it may be equal to the basic size or it may be slightly deviating from the basic size. But do we accept that deviation? So that will be decided by this tolerance zone. So narrower is the tolerance zone, more precise manufacturing process is needed, more precise tooling, more precise jigs and fixture are needed to create that product, more will be the cost of production of that any product. So this is how there is always a optimum tolerance level which is not too high, because if you create very tight tolerances, the cost of production will be too high, and then the cost of the product will be also very high, and then accordingly the customer whosoever is taking that product is also paying a higher cost. But higher tolerance may always not imply improved performance. So generally a satisfactory level of performance may be achieved by a okay type of tolerance product. So I am just stopping here to just again summarize the gist here. So we in the production drawing section, we are going to deal with how to give this tolerance, how to give this deviation on the drawings, and what is the meaning if you are given a production drawing of any product. So how to read that drawing, how to draw inferences from that drawing, how to decide what is the tolerance level, what is the basic size, and so on. These type of details, how to deduce it from the drawing. So this is all what we will be dealing in the production drawing section. I am not jumping into the slides today because I wanted to start it in the next, but since we had some time, I have given a basic introduction. So if any of you have doubt with the basic introduction, any question with the basic introduction of production drawing, you may please feel free to discuss it now. Yes.